going to write your essential question up here because I didn't leave us a space for it. So today we're going to talk about linear systems. You did this in Algebra 1 as well. And so we're just going to do a little review. So the question is, how do you solve systems of equations algebraically what kind of solutions are there? Okay, so we are going to use a ruler when graphing to make your graph exact. So make sure you have a ruler. And our first part of this review is to go ahead and graph. We have two separate equations, right? So we have y equals x minus 6 and y equals negative 3x plus 2. Okay, so let's start with y equals x minus 6. Well, I know that this is my y-intercept, so my y-intercept is 0, negative 6. And I also know my slope. My slope is right here, right? So my slope is equal to 1. So I can get 2 points here. I have a point that I can start with, 0, negative 6. So I'll put a point at 0, negative 6. And from there, I can use my slope, and slope is rise over run. So up 1 over 1. And maybe do that a couple times so we can get an exact graph. Okay, and then I'm just going to draw a line. Trying to make my graph as exact as possible. Okay, so this is y equals x minus 6. Especially when you're graphing more than one, you want to label them. The second equation has a y-intercept of 0, 2, and a slope here of negative 3, or negative 3 over 1. So I go up to my y-intercept, which is 0, 2, and I go down 3 and to the right 1. So there's lots of ways to think about negative slopes. Down 3 to the right 1. Okay, so think of that negative as down 3. You could also go, let's see, you could go up 3 and backwards 1. Right, so I could go up 3 and backwards 1. So I'm putting that negative to mean backwards. Either way, these are both negative 3. So you can do it either way. So I'll go down 3. Let's see, 1, 2, 3, and over 1. I'll also get another point by going up 3. 1, 2, 3, and left 1. So those are just a couple of different ways that you can think of it. People get confused sometimes about that. And I'm going to try and make my graph as perfect as possible. Okay, so we graphed both, and let's see, I'm going to write this equation right here. All right, what is the solution of the system of equations? AKA, where do the two lines intersect? Oh, and maybe I should back up a little bit. A solution of a system, so system of equations is basically two or more equations in the same coordinate plane. So here we have a system of equations because we have 2. Sometimes you'll have 3, sometimes you'll have 4, sometimes you'll have 5, okay, and so on. All right, so that's a system of equations. Now we're looking for the solution, which is basically where the 2 lines or 3 lines or 4 lines intersect. Okay, and we'll write it as a point. So the solution is going to be some point that's got an x and a y coordinate. All right, so this point right here is where they intersect, and that point is 2, negative 4. So 2, negative 4 is the solution to this system. Now, let's try doing this. Let's try solving the system of equations algebraically. So we'll substitute one of the equations into the other. Okay, so we're going to use that substitution property to substitute one of my equations in for the other. So notice, I'll rewrite the equations here. I've got y equals x minus 6 and y equals negative 3x plus 2. See how they both equal y? So I can take one of these values of y, with, like for example x minus 6, and I can substitute it in to the other. Okay, that's going to end up giving me x minus 6 equals negative 3x plus 2. Okay, so I did that. Solve for x. Okay, so we're going to go ahead and we're going to solve for x here. So I'll add 3x to both sides. I like to get my x's all on one side. Thinking about getting x by itself. Okay, so I'm going to add 6. Now thinking about still getting x by itself, so it's being multiplied by 4, so I'm going to divide both sides by 4. Okay, so I solve for x. Okay, so that's the x value where they, look, that's the x value where they intersect, right? And now, the next thing we're going to do is we're going to substitute x back into either of the original equations and solve for y. So pick one of these two equations. I'll take the first one. I'll substitute that back in. So I end up with, y equals negative 4. Notice that's the y value of my solution. So this is how we do it algebraically using substitution. Okay, so let's see. So this goes ahead and shows us that you don't even actually have to graph these if you're using your algebraic properties to substitute one of the equations in for the other. So here we use substitution to solve this algebraically. So this can be solved either by graphing or in a case like this, substitution. Now, me personally, I'm not going to graph. I'm usually not given some beautiful graph paper that I can graph this really neatly on. And it takes a long time, and it's not always exact. Using substitution is exact. Now, using substitution is not our only way of solving these, though. Okay, we'll talk about that in a minute. So what happens when we graph? Let's see. Negative 2x plus y equals 4, and y equals 2x plus 1. So we're going to graph those on the same coordinate plane. Now the second equation, this one's pretty simple to graph, right? I can see that I've got a y-intercept of 0, 1, and I've got a slope of 2. Okay, so I'm going to graph that one. So 0, 1. And then from there, I'll go up 2 and over 1. And I'll do that a couple times, just so I can try and make this as exact as possible. You really only need 2 points to graph a line, but I'm trying to make sure that these intersect, these lines, or if they do intersect, I'm trying to make sure that they're exact, so that way I don't miss any intersections, I should say, or I get them correct. Okay, now, the problem with this one, notice it's not in slope-intercept form. So right now, I'm not going to teach you every different type of form. I'm just going to go ahead and review slope-intercept form. So if I have an equation that's not in slope-intercept form, I can get it into slope-intercept form. Remember, slope-intercept form is this. So in order to get it into slope-intercept form, we always need to solve for y. See how y is all by itself? That means that y is solved for. So I'm going to come over here, and I can easily get y by itself by adding 2x to both sides. So I have y equals, I'll put the slope piece first, 2x plus 4. Well, now I know that my y-intercept is 0, 4, and my slope is 2 over 1. Okay, so let's see what we get here. So I'm going to start at 0, 4, and I'm going to go up 2 over 1. I'll do that a couple times so I can make it as exact as possible. Oh, and I didn't label my lines. I'm going to label my lines now too. So this one was y equals 2x plus 1. And the other one was negative 2x plus y equals 4. Or you could write it this way too. Well, darn it, they didn't intersect. So is there any solution here to this system of equations? So what do you notice about these two lines? How do they relate to each other? So I notice that these two lines on the graph, they're parallel. Now, how do they relate to each other? Well, if I look at them both in slope-intercept form, what do you notice? Well, parallel lines have the same slope. We've talked about this before, right? So these have the same slope. Okay, B is asking, what is the solution of this system of equations? AKA, where do the two lines intersect? Well, what do you guys know about parallel lines? Parallel lines never, ever, ever touch, right? They have the same slope, which means that they rise and run the exact same amount, both of them at the same rate. They're changing at the same rate, so they'll never, ever touch. Okay, so write it as a point, x, y, but there won't be any intersection, right? So if they do not intersect, then that means that there is no solution. So for this one, there is no solution because they're parallel lines, right? There's never going to be a point where they intersect. Okay, so now we're going to go back and we're going to use substitution to solve the system. And we should get a false statement. Okay, so two equations here. I'm going to go ahead and use the two original so that way you can see that you don't necessarily have to change the order. You don't have to put this into, you don't have to put this into slope-intercept form. You can if you want in order to use substitution, but you don't need to, right? Because I have a value here for y. So one of these is already solved for y. It's already put in slope-intercept form. So I can plug or substitute this in here for y. So I can just go negative 2x plus, and now the value that I'm plugging in for y is 2x plus 1. So I'm going to put it in parentheses. I'm plugging it in, equals 4. Now notice I've got a 1 out here in front. So in order to get rid of these parentheses, I'm going to distribute this positive 1. So I'll have negative 2x. Distributing a positive 1 doesn't really do anything. I'm making a big deal about this for a reason. If this was a negative, this would change things, right? There's nothing to change here. So it's really just going to give me the exact same thing. So it's plus 2x plus 1 equals 4. Combine like terms on each side. So I notice on this side that I have some like terms. I combine those. Negative 2x plus 2x. Well, that's 0, right? There's nothing here. So these actually cancel out, and I'm left with 1 equals 4. Notice that's a false statement. 1 does not equal 4. So if you have two equations of lines and you're trying to solve the system and you do so algebraically and you get a false statement, that means that they are parallel lines and therefore there is no solution. They never ever touch. All right, so I think on this page, I'm going to highlight some of the important stuff here so it kind of pops out at you. So, parallel lines, same slope, no solution, and if you solve it algebraically, you're going to get a false statement. Like 1 equals 4, or 3 equals 2, or 0 equals 5. Okay? So when solving a system of equations, you will know the graphs don't touch or are parallel, and the system has no solution when you get a false statement. So that's important. That's basically what all of this says. Graphs don't touch, so they're parallel, and the system has no solution when you get a false statement. So all that stuff basically means the same stuff. Okay, this is all about parallel lines. All right, moving on. Now we're going to graph these two lines. Okay, So the first one here, again, I'm going to put that into slope-intercept form. It's going to make it a little bit easier to graph. Okay, so got to get the y by itself. So I'm going to add 6x to both sides. I end up with 2y equals 6x plus 4. Right, I'm trying to get it into slope-intercept form, which is why I put the 6x first, because that's my slope. Right, so the mx, right, that's the first term. Okay, and then I got to still get y by itself, so what do I need to do now? Well, 2 is being multiplied to y, so to undo that, we divide both sides by 2, the entire side. Okay, so I get y equals, and then remember, this whole side's being divided by 2, so I put the 2 into 6x, and I also divide it into 4. So it looks like I get 3x plus 2. Okay, so we're going to go, let's see, so my y-intercept here is 0, 2, and my slope is 3, or 3 over 1. So you graph your y-intercept, and then you use your slope to get another point. 1, 2, 3 over 1. Or, just to remind you guys, I could also do 3 is the same as negative 3 over negative 1, right? So I could also go down 3, 1, 2, 3, and backwards 1. Doesn't that still have a positive slope? Okay, so I'm just getting a few points there, so that way this is nice and exact. Yes, 2 points form a line. But if we want our graph to be exact, we're going to use maybe more than 2 points. All right, this other equation here, well, again, my y-intercept, that's 0, 2, and my slope is 3. What the heck? They're the exact same thing, right? Oh, actually, I could have seen that right back here. These are the exact same line. So that would mean I'd put the exact same line right on top of it. They call that coincident. I don't know. I just say it's the same line. Okay. So what do you notice about these two lines? And how do they relate to each other? So they are the same. Right? They're the same line, which basically means they have the same slope, same y-intercept. They were just written in different forms. Okay, what is the solution of this system of equations? AKA, where do the two lines intersect? Where do these two lines intersect? They intersect at every single point on the line. How many points are on a line? These lines go on forever and ever in both directions. So how many points are there? Well, there's infinite points, right? Okay, so what is the solution of the system of equations? Where do they intersect? Well, they intersect at all the points on the line. Write it as a point? I can't. There's too many. I'll be here until I die. Okay, so if they end up on top of each other, it means that they are the same line and have infinite points in common or infinitely many solutions. Okay, so this basically, what we can say is that for this, there are infinitely many solutions. Now, infinite, I use like a sideways 8. That's like the infinity sign. So you can also use that. Okay, the last part of this, we're going to use substitution to solve the system. So I'm going to take the original two equations. One of them is already solved for y, and I'm just going to substitute it in for y in the first equation. So first one was this. The other equation is this. See how this one's already solved for y? I'm going to take what y equals, and I'm actually going to just plug it in right there. So this is negative 6x plus 2 times the quantity, 3x plus 2, that's what I just plugged in. I substituted that in for y, equals 4. Okay, so we got negative 6x. Now I've got to distribute this 2 because 3x and 2 are not like terms. So I'll distribute. Plus 6x plus 4 equals 4. Combine like terms, and I have like terms right here on the left-hand side. Those cancel out, and I'm left with 4 equals 4. Okay, what do we notice about this? This is a true statement. So notice it says here, you should get a true statement like 5 equals 5, or 0 equals 0, or 4 equals 4. And when solving a system of equations, you will know the graphs are the same line and have infinite solutions when you get a true statement. Okay, so this is infinitely many solutions because we ended up with a true statement. So that's how we know that they are the same line. So once again, I'll go through this and I'll highlight the important stuff. Okay, so we have the same line, which means we have infinitely many solutions. And when we solve the system algebraically, we get a true statement. Okay, you know the graphs the same line and have infinite solutions when you get a true statement. So just to summarize, we did 3 different types of systems with 3 different types of solutions. So the first system, the lines actually did intersect at one point. So this ended up being our solution. We got one solution. Okay, I'm going to actually write that. So this one was one solution, and that solution was a point. Okay, so one solution is the point where they intersect. Maybe we can highlight this. What is the solution of the system? AKA, where do the 2 lines intersect? So solution of a system is where the 2 graphs, in this case lines, intersect. Okay, we use substitution property to help us with that. When we have parallel lines, we know that they're parallel because they have the same slope. Okay, they're going to have different y-intercepts though. Notice this one had a y-intercept of 1, this one had a y-intercept of 4. So they're not the same line. Okay, parallel lines have no solution, and if we solve the system algebraically, we're going to get this false statement. Anything that's really not equal on both sides. And then the last type is when we have the same line, and again, these had the same exact y-intercept and the same slope. So the exact same line, infinitely many solutions, and we get a true statement if we solve it algebraically.